All right, as we continue on with stereochemistry, let's take a look just real briefly at synthesis, something we've said before, but it's very important. It's one of the big problems we have in organic synthesis is when we have an achiral starting material, when our reactants are not chiral, there are no chiral carbons, and you generate a chiral carbon, you make a chiral product, you're going to get the racemic mixture of the two enantiomers. So this represents a problem, as we said, because in general we only want one of the enantiomers. As we, for example, your amino acids in your body, all your amino acids are chiral except for one. Glycine does not have a chiral carbon, but all the others are chiral, and they are all the L isomer. Every amino acid in your body is the L isomer. All the chiral ones, which are 19 out of the 20. And so if you want to generate some amino acids and you start with achiral reagents, when you generate the amino acid, you're going to have a racemic mixture of the L and the D products, and then you only want the L, and separating out all the L amino acids from the D is tough because all the methods we've looked at so far, distillation, extraction, recrystallization, they just don't work to separate enantiomers. You just have to say, okay, let me find something that interacts with one of them, another chiral molecule that'll interact with one of the isomers and not the other to try to get rid of it. Okay. So trying to get around that rule, making a stereoselective reaction, one that's what we would call enantioselective, only makes one of the enantiomers, is very difficult to do. And in fact, Nobel Prizes have been awarded for the ability to make one enantiomer over the other, because we just can't get around this rule. If you start with achiral starting materials, you cannot have chiral products without enantiomers. Another way of saying this rule is if your reactants are not optically active, then your products cannot be optically active. And that's how we're going to go with it. So if your reactants do not rotate plane polarized light, they're not optically active, then your products cannot be optically active either. And as we know, racemic mixtures are not optically active. Very important thing with this rule. If you start with optically active reactants, you can make optically active products. You can make non-optically active products. This rule is only in one case. If your reactants are not optically active, then your products cannot be optically active. That's how that rule goes. So let's crank it up a notch. We've been looking at molecules with one chiral carbon. What if we have molecules with more than one chirality center? What if we have two chiral carbons? For example, let's look at this beast right here. If we look at this molecule, we can say, all right, how many chiral carbons does this one have? And this is a good exercise to go through. How many chiral carbons? Well, this is a CH3, cannot be chiral. CH2 cannot be chiral. What's on this carbon right here? Well, a bromine, a hydrogen, an ethyl, and the ethyl with a bromine. And an ethyl with a bromine is not the same as a regular ethyl, so that is 4 different substituents on this carbon. Bromine, hydrogen, this half the molecule, and the other half the molecule that's not the same. So this is a chiral carbon. You can see that this carbon here is also chiral with 4 different substituents coming off that carbon. When you have more than one chirality center, 2 in this case, the total number of stereoisomers cannot exceed 2 to the n, where n is the number of chirality centers. That's the 2 to the n is the maximum number of stereoisomers. Okay, here we have 2 chiral carbons, 2 stereocenters. Therefore, 2 to the n is going to be 2. 2 squared is 4. So with this molecule, we would expect a maximum number of 4 stereoisomers. It's possible that we might have less than 4, but the maximum number we can have is 4. And we will show you how we might get less than 4. What's the best way to do it? How do we draw these four possible uh, chiral molecules, or four possible stereoisomers? Well, best way to do it. Write as many of the carbon atoms in the plane of the paper as possible. Draw the molecule in the eclipsing conformation. What we're saying is the two chiral carbons, the substituents coming off the two chiral carbons, you want them to be eclipsing. That is the best way to do it. You don't have to do it that way, but it's a heck of a lot easier to see what's going on if you do it that way. So, once you've done that, you draw the enantiomer, the mirror image. So here's my molecule here. Note I've got a bromine down and a bromine up. I want these eclipsing each other. So I'm going to rotate my bond here. So this bromine is going this way. This hydrogen is up and back. This bromine is up this way. This hydrogen is back. Note I have eclipsed my bromines. So that's the first thing to do, is draw this with eclipsing bromines, put it in an orientation where you can do that. All right. Then you draw the mirror image of it. Just, okay, here's my mirror. This molecule 2 is a mirror image of this molecule 1. And the question, are they the same thing? Is there any way to rotate this guy and get this guy? Well, note if I rotated this 180 degrees, if I just flipped it over 180 degrees, I do not get this one, because rotating this molecule 180 degrees puts this ethyl over here and puts the methyl right, but rotating this 180 degrees puts the bromines going back. And in this one, the bromines are coming out. So note, rotating 180 degrees does not give me this. This guy here is the mirror image, and it's not the same molecule. So this is these two are enantiomers. So after you've done that, what you want to do is flip the stereochemistry configuration, the stereochemical configuration, about one of these carbons, but not the other. So what you do is invert the configuration around one carbon, and I have chosen to do this carbon here. So I'm going to redraw this whole molecule, except instead of the bromine out and the hydrogen back on this one carbon, I'm putting the hydrogen out and the bromine back. Note, I leave that second chiral carbon the same. I do not flip the configuration on that second chiral carbon. So now, is this one that I have made the same as any of these? Hopefully you can see it's not, because the bromines aren't eclipsing each other anymore. So this is different, and there's no way to rotate it to get the bromines eclipsing and have everything else the same. So this is a different isomer, and draw the enantiomer of it. And when we draw the enantiomer of it, the mirror image, is there any way to rotate this one and get this one over here? Hopefully you can see it is not, because note this bromine here is coming out at us on the carbon connected to the methyl. If we rotate it, here's a carbon connected to the methyl, the bromine is still coming out on us, but if we rotated this, that bromine should have been going backwards if we actually rotated the molecule. So rotating this molecule does not give us this molecule. Only this is only the mirror image of it. Therefore, these two are enantiomers. Well, okay, what's the relationship then between these two then? Here's the deal. They are not mirror images of each other, but they're also not superimposable. So they are stereoisomers, but they're not mirror images of each other. That means they are diastereomers, because diastereomers is any stereoisomer that's not part of an enantiomeric pair. That's not an enantiomer. These two are enantiomers. These two are diastereomers. Relationship between 2 and 3 are diastereomers. 1 and 4 are diastereomers. 2 and 4 are diastereomers. And note, I had mentioned before that one way to draw enantiomers is to just draw the mirror image that we did here and like we did down here. The other way to draw enantiomers is to switch two groups on both chiral carbons. So if you were to switch both of these two and both of these two, you would find that you had made this molecule. Go ahead, try that. Do it with your models, do it with your brain. Put the hydrogen coming out and the bromine back on this carbon. put the bromine back and the hydrogen coming out on this carbon. Just switch the two groups on both carbons, and you'll note if you do that, switch the two groups on both carbons and then rotate 180 degrees, you do get this molecule. You get this one. So one way to make enantiomers when you have two chiral carbons is just to switch two groups on both chiral carbons. If you had three chiral carbons, you'd switch two groups on all three chiral carbons. The way you make the diastereomer, if you have more than one chiral carbon, is just to switch two groups on one chiral carbon, but leave the other chiral carbon the same. All right. Now, note that we started up here. Okay, we had two chiral carbons, so n is 2. 2 to the n means we can have a maximum of 4 stereoisomers. Here we found we have 4 stereoisomers, and none of them are the same. So we have the actual 2 to the n, we have 4 stereoisomers. But if we did the same type of treatment with 2,3-bromobutane, note we still have 2 chiral carbons here. And so if we did the same treatment, here's the 2 bromines. One's coming out at us, one's going back. 2 chiral carbons. If we rotate this 180 degrees, it's not the mirror image. So, okay, we make the mirror image. Rotating, there's no way to rotate this one and get this one if you can't do it in your head yet. And yet is the key word. If you can't do it in your head, try it, make your models and try it. If you rotate this one, you cannot get this one. Therefore, these two are enantiomers, non-superimposable mirror images of each other. But note, if you rotate or switch two groups on one carbon to make the diastereomer, you can do that. I've decided to take this carbon here, put the bromine coming out and the hydrogen back, but I left the first carbon the same. This is the diastereomer of these two, but note, if you were to do the mirror image of it, you would get the same molecule. The mirror image of this is this. They are the exact same molecule. So this one has no mirror image that is different. It does not have a non-superimposable mirror image. If this guy, even though it has 2 chiral carbons, does not have a non-superimposable mirror image, it in itself is not chiral. Recall, chirality is a property of the entire molecule. The way we look for chirality is by looking for chiral carbons, and here we have an example of a molecule with 2 chiral carbons, but the molecule as a whole is not chiral. When you have that situation, we have chiral carbons, but not a chiral molecule because we have 2 or more chiral carbons. Since it's not a chiral molecule, it is not optically active. We call this a meso compound. And the interesting thing about these meso compounds is when you look at them, instead of drawing the mirror image, or if you look to see that the mirror image is the same molecule, one way to tell is, do you see a mirror plane in the molecule? Is one half of the molecule the mirror image of the other half? Is one side the mirror image of the other side? If you see in your molecule one side is a mirror image of the other side of the molecule, that means you have a meso compound, and it's not optically active. It is not chiral, even though it has chiral carbons. So that's the thing to look for in meso compounds, a mirror plane of symmetry within the molecule. The problem with this that you're going to run into is that humans are very, very good at looking for mirror planes when they are what we call vertical mirror planes that go up and down. Just look around the world and you'll see many of the objects that you normally see have what we call mirror plane symmetry, vertical mirror plane symmetry, where the left half is a mirror image of the right half. Heck, you are a meso compound. The left half of you is a mirror image of the right half of you. So we are good at seeing this. What we're not good at seeing is when the mirror plane is not vertical. For example, if I were to draw this molecule here, we're getting a little bit ahead of ourselves, but that's all right. This cyclohexane, if I were to put a methyl group coming out here and another methyl group coming out here, I will note that I have 2 chiral carbons. This carbon right here is chiral because it has 4 different groups coming off of it. It has a methyl, a hydrogen. As we go around the ring this way, it is different than going around the ring this way, because first over as CH2s, and then here, oh, this is a CH2 and this is a CH. So going around opposite ways gives you different results. So that's a chiral carbon here. This is also a chiral carbon here. So we have two chiral carbons. We have four maximum stereoisomers. Question, is this a meso compound? Is there a mirror image of symmetry in this molecule? And hopefully you can see that, yes, there is. You can divide the top part of the molecule is a mirror image of this part of the molecule. And if you can't see it, if I can just rotate the paper, now can you see that one side is a mirror image of the other side when we arrange it vertically? But it's tougher for humans to see it when it's not vertically. When it's on the diagonal, it's tougher for us to see it. So you have to make sure you are looking properly. Make sure you look at all different orientations of that mirror plane to look for these meso compounds. All right. So, yeah. Naming these still follows the same Kahn-Ingold-Prelog rules. I strongly recommend when you have many carbons or a chain, if you have 4, 5, 6 carbons, make sure the carbon chain is in this, going in the plane of the paper like this. Even if you've drawn the molecule differently, make your carbons in the plane of the paper. Make them eclipsing. Try to eclipse as many things as possible. So it's actually usually better, instead of going up, down, up, down, up, down when you draw your chain, it's usually better to kind of draw it like this. So you can get eclipsing things, so you can tell if it's a meso compound. And when we look at this, just plain old Kahn-Ingold-Prelog rules. If we look at carbon number 2 here, we see, okay, it's got a hydrogen on it. Well, that's obviously priority 4. It's got a bromine on it. Oh, that's going to be priority 1. Priority 1 is the bromine. We see that this carbon has 3 hydrogens on it, so this is HHH. This carbon here has a bromine, a carbon, and a hydrogen, so that's BRCH. Definitely, this is priority 2. So we have priority 1 is the bromine, priority 2 is this carbon, priority 3 is this carbon. Hydrogen's already going back, therefore we have a rotation from 1 to 2 to 3, which is clockwise, so this is the R isomer. This is R. Note, the nice thing is when you draw it in this configuration, your hydrogen will either be coming out at you or going back towards you, going back away from you. So it's very easy to determine the next group. So when I'm looking at this one, it's like, okay, the hydrogen's coming out at me. Now, one thing you could do is try to rotate the molecule to get that hydrogen going back, because that's what we have to do. But I'm going to employ our other little trick. I'm going to look at this and say, okay, I can see that the bromine is priority 1, of course. We can see that this is priority 2 here, and over here will be priority 3. The hydrogen is coming out at me. I'm not going to put it backwards. I'm going to draw my circle from 1 to 2 to 3 in that direction. Now, since it is going counterclockwise, this would normally indicate that this is the S configuration. However, I did not put my hydrogen back. My hydrogen is coming out instead of going back, so I know that this counterclockwise circle is wrong, that the real one should go clockwise because I didn't put that hydrogen back like I should have. Therefore, instead of S, this actually is the R isomer also on carbon 3. So when you draw the name of this, note there's a bromine on 2, a bromine on 3, so it's 2,3-dibromo butane because there's 4 carbons, but we need to indicate the RS configuration 2R, 3R dash 2,3-dibromobutane, and that's how we would name this. And real quick, the last thing for this video is when I've been saying to draw it in this configuration right here, what I'm really doing is drawing a Fischer projection. I'm because I've got a Fischer projection on its side when you draw it this way. When you draw it into this eclipsing conformation, it's a Fischer projection on its side. All you have to do is rotate it so that the carbon chain is vertical and the other groups are coming out at you horizontal, and you've got the Fischer projection. It turns out that trying to find meso compounds is very easy with a Fischer projection because you could actually see. You can tell here that there's one side of the molecule is there's no way to have one side be the mirror image of the molecule. If my mirror plane is going this way, we can see that the mirror image of a bromine is not a hydrogen. If my mirror plane you try to draw this way, you can see the same thing. We've got a bromine and a hydrogen, not mirror symmetry here. So this is not a meso compound. So get used to drawing Fischer projections and changing a Fischer projection into this and changing this into a Fischer projection. Make sure you can do that in your head.